Robot Talk is the podcast that sits down with roboticists from around the world and asks them the questions you always wanted answered. Like, can the robot change shape? And how does that thing work? Hello everyone! Welcome to Robot Talk. I'm your host, Claire Asher, and this week's episode is about building more intelligent robot bodies. I'm finding out how geometry, maths, and the ancient art of origami can inform robot design. Before that, I'd like to remind you to check out the Robot Talk shop at robottalk.org/shop, where you can get your hands on some awesome Robot Talk merch. Share your love for robotics with the world with one of the Robot Talk t-shirts, stickers, or mugs. So, without further ado, let's get on with this week's interview. I recently had a really interesting conversation with Chenying Liu from the University of Oxford about how a robot's physical form can actively contribute to sensing, processing, decision-making, and movement. Today, I'm talking to Chenying Liu, a junior research fellow at the University of Oxford, whose work focuses on embedding intelligence directly into robot bodies to generate useful behaviours. Hi Chenying, it's lovely to have you on the podcast.
Hi Claire, thank you so much for having me.
So your research is exploring how the physical form of a robot can help it to sense, move, process information, and make decisions. So to get us started, can you give us a little bit of an overview of what you're working on at the moment?
Okay, so my research is really about making robot bodies themselves more intelligent. Traditional robots rely heavily on a central brain. You can imagine it's the algorithm that processes the sensor data and then tells the motors of the robots what to do. So basically, the body is just executing those commands. Yeah.
Mm-hmm.
What I'm exploring is a slightly different idea. Can the body itself take on some of that intelligence to process information? So my current work has two main directions. The first is designing new mechanisms or structures where the robot bodies with specific geometries that naturally produce useful behaviors or useful movements. This can combine strength and load-bearing capability with adaptability, which is often a trade-off of the rigid and soft robotics.
Mm-hmm.
The second is integrating some unconventional materials into the body. For instance, the materials that can sense things like humidity or temperature and respond directly without needing electronics. This is especially useful when there is some harsh environments that the traditional electronic sensors just fail. A lot of this is actually inspired by biological organisms in nature.
Mm-hmm.
For example, you can think about a worm. It doesn't need a detailed map of its environment to move. It simply contracts and relaxes its body, and the body just passively adapts to the terrain. The behavior actually emerges from the interaction between the soft body and the environment without a central community. So the idea is to redistribute the intelligence between the body and the brain rather than concentrating all of the intelligence into algorithm. So by co-developing the body and the brain together, the body can do some way of thinking to make the robot more intelligent.
Yeah, it's really, really cool. I guess it has a lot of advantages because if the body is doing some of the thinking, as it were, then you're saving on kind of computational power and probably also responding quicker.
Mm-hmm. Maybe I could give an example to explain this idea further. Mm-hmm. For instance, I have designed a robotic gripper, and one mechanical phenomena I used in it is called mechanical bifurcation. This means the structure can follow different motion paths without increasing the overall degree of freedom. That's usually a key deciding factor about how many motors are needed.
Right.
Then the robot behaves based on how it's loaded to switch into different motion paths. So in the end, with only 2 motors, the gripper can reach up to 8 grasping motion modes, which is really, really unusual for traditional robotic hands, which would require a lot more actuators and sensors to achieve those 8 grasping modes.
Mm-hmm. So it kind of just reconfigures its shape to do different grasps.
Yeah.
That's really cool.
And the shape reconfiguration is based on mechanics-guided behavior rather than purely electronics control.
Okay. Can you explain what bifurcation means for people who maybe aren't familiar with the term?
That's a good point. Bifurcation is a state of a system where it can choose which path they want to go. Imagine that you are at the cross of a road. You have 4 paths to go. At that specific state, you have 4 choices you can make. But once you make your choice, you are on a single path.
Mm-hmm.
And in that single path, you don't have to any extra control to change direction or whatever, because your motion is already guided by that path. So what you do is that you only choose the path at the decision point, which is a bifurcation.
Right.
Does that make sense?
Yeah, that makes sense. So, I mean, if you're designing the shape of a robot so that it can, respond or show some intelligence, does that mean that the robots have to be quite task specific? Does it kind of limit the scope of a robot to be very much designed for one task, if that makes sense?
Oh, I see. That's a very, very good question. Yes, at the moment, people usually design so-called intelligent robots for specific tasks. Mm-hmm. But there is an emerging trend to do multimodal robots from a similar point of view. For instance, you could have a robot that crawl on the island in dry environments, but it has a special material that can be triggered by humidity change. For instance, inside the water, the robot can automatically change its morphology into another shape, which makes it suitable for swimming. This is possible by design, but as an emerging field, I think there are a lot more work to do and a long way to go on this direction to make the robot truly dexterous and adaptable to different tasks. Yeah. But I believe this is also a challenge for the traditional robots we talk about, made from the rigid links and motors.
Yeah, absolutely, yeah.
Yeah.
That's really interesting. So one aspect of your work involves taking inspiration from origami, the traditional Japanese art of paper folding, to design more intelligent robot bodies. But it's not really practical to make robots out of paper. So how do you translate the principles of origami into more robust materials that you might want to make a robot out of, like metals or plastics?
That's a really, really good question. Because you're absolutely right. Paper is not really suitable for engineer use. So what we take from origami is actually its geometry rather than the material.
Right.
It's popular as a paper folding art, but we don't take paper. We only take the folding, which is the geometry mathematics behind it. In traditional paper origami, you can think about the structure as some thin but relatively rigid facets connected by very thin rotational joints, which is the most fragile part. And mathematically speaking, this one behaves like something we call spherical linkage. This means all the creases of the folding joints of the origami intersect together on a single unit.
Okay.
This is interesting because we can analyze the structure using mathematics to describe how it behaves. But when it changes to material of a certain thickness, rather than paper, because paper is essentially zero thickness.
Yeah.
The same change, because we have to replace the folding joints either to the top or bottom surface of the materials.
Right,
there is an offset. That just changed the mechanics quite a lot. So it's very likely the structure is no longer able to move because it's no longer a mobile linkage as we described mathematically for the zero thickness paper pattern. In this case, because there is an offset in the folding joint, we usually model this as something called spatial linkage in mechanical engineering. What we do is try to analyze the mathematics behind it to see what kind of geometry design, what kind of offset, what kind of panel angle could make the linkage still mobile. There are lots of permutations, but it's possible to go through it mathematically to see which patterns are still feasible and which patterns are not. And in the end, we can produce controlled interesting motions from those called thick panel origami with some durable and stronger materials like plastics, wood, or even metal. And the next thing is, once you have the mathematical frameworks that are used to describe such origami, we can simply do a CAD design in the computer and print the whole structure in a desktop 3D printer.
That's awesome, yeah. So, I mean, what is your process for kind of going from like origami inspiration to robot? Do you see like a cool origami design and think, oh, I wonder if I can do something with that, and then kind of do the maths and see whether it can be applied? Or do you start from a robot problem and then search for like origami patterns that might help you?
Actually, I do it from two ways. Yeah, because the first one is a very popular trend at the moment. People start with some artistic origami and see how we can turn it into our engineering prototype and to generate some interesting behaviors and see what kind of robots could be the most suitable applications. That's one popular trend. And I have actually used Questling origami, a very traditional origami that can twist into a conical-like shape to create wrist orthotics. It's interesting, but my real interest actually lies in designing new origami structures that can suit robot needs. Because if you think about what robots want to have, there are a few things. You want it to be manufacturable. So I designed the thick panel origami that can be 3D printed easily. And the robot wants to have some dexterity. This means I want to have something to perform different tasks, have different grasping modes, like the gripper I mentioned, this or that. So I designed some origami from a single pattern. It can leverage some mechanical properties to change its motion mode. And we also want to have the robots to be adaptable to the environment, to mimic some of the soft-bodied properties of the soft robots. So I can modify the design of origami, for instance, its hinges, so that we have some extra compliance or flexibility inside the structure.
Amazing. So you've mentioned that the weakest point is obviously that fold. And we have a related audience question from Elodie on Twitter who says, how do you prevent stress cracks at the creases during high cycle folding?
Oh, yeah. That's a very classic challenge for origami, even at the moment. The creases are where the stress concentrates because, as I mentioned, it's combined of rigid facets connected by the creases. The facets don't deform too much. For rigid origami, it doesn't deform. For non-rigid one, it expands slightly, but no huge deformation. But for the creases, it has to rotate by either 180 degree or maybe double it. It's a challenge, but it's still solvable. There are a couple of ways I could think about to address this. One thing is the material choice of the joints. For instance, we could use fatigue-resistant fabrics like certain polymers.
Okay.
Yeah, like your clothes. The fabric is a really, really good thing to undergo repeated folding and unfolding. Another thing is to replace the sharp creases, the thin creases, with some engineered joints. You can imagine a minimized version of the door hinge. You know, the door undergo repeated folding and unfolding thousands of times, thousands of cycles, but it's still working perfectly well. And this idea can be borrowed to origami design as well.
Yeah, that's really interesting. So, how do you think that embedding intelligence into physical structures of robots can help us build robots that are more efficient and more resilient?
Yeah, as I mentioned, for some mechanical design, you could reduce the number of motors or sensors you want to use in the gripper. as explained in the previous Reaper example.
Yeah.
But the principle goes beyond the grasping task. For instance, recently I have developed a millipede-like robot using the origami principle. The millipede is a worm-like arthropod that can change its shape into some coil, wave-like, and triangular shape. And in robotic concept, we call this reconfigurability. Traditionally, people use different modules, connect them together, and if they want the robot to change the morphology, the modules have to disconnect and reconnect again to form something new.
Yeah.
But in my case, it doesn't have to do that because the origami naturally generates some mechanics-guided, bifurcation-guided behavior to mimic the coil, wave, and triangular shapes of a millipede, which helps the robot to behave more robust because it eliminates the disconnection and reconnection process.
Okay. Yeah, the millipede robot sounds really cool. What kind of applications do you think that could be used for?
I'm trying to target some disaster rescue and response for the millipede-like robot because it can crawl and it can change its morphology. So this means the robot can actually navigate through some very confined space more efficiently by changing its morphology.
Yeah, that makes sense. You were also interested in how unconventional materials can contribute to robot design. So what is the strangest material that you've used to build a robot?
Oh, that's a very fun one. Well, I talk about the plastic I did. I talk about maybe wood and metal I use for origami and the robots. Actually, I could think about two materials that can be strange. One is inflatable fabrics, like the one used in Airbus. I use that to make some wearable robots for people to dress on their wrist, on their arm, which is interesting.
Yeah.
But the other one could be more weird,
Okay.
which is an ongoing project I'm focusing on, which is to incorporate some cells into robots. Because, traditionally we power the robots using motors and something else, but cells, it could be about motors to generate the force, create some folding-like motion for robots or origami. And there's lots of ongoing work, but it opens up the idea of perhaps hybrid robots. So maybe cell could be the most strange material I would be working for robots.
Yeah, definitely. I've interviewed a couple of people who've worked on biohybrid robots, and it's kind of mind-boggling the possibilities that you can achieve when you start mixing synthetic and living materials.
Yeah. It means that you generate some human-created things from the living cells, combine them together. Oh, it's very exciting.
So you mentioned it could be used, like living cells could be used to sort of power the movement of the robot. Would that be like kind of like a microbial fuel cell, or would they be like physically moving to move the robot?
I would say physically moving. What I'm working on is to try to incorporate some muscle cells from mouse to generate the folding behavior of some classic origami patterns, for instance, the Murari. And imagine there are two plates connected by a hinge, a folding hinge. And once you attach a muscle cell on top of the plate, of course, you have to ensure the adhesion is well. And by certain trigger, maybe electrical stimuli, the muscle contracts and the plate just naturally folded. And once the muscle cell is relaxed, the plate opens up.
That's incredible. Absolutely fascinating area of research. There's just so many possibilities, and it's really cool.
Thank you.
Chenying, it's been fascinating chatting to you today. I've been speaking to Chenying Liu from the University of Oxford. Thank you.
Thank you.
Thanks for listening. If you enjoy Robot Talk, I'd really appreciate it if you could share the podcast, subscribe, and leave a review. And check out @Robot Talk Pod on social media to see a photo of the Origami-inspired millipede robot that Chenying and I talked about. Next week, I'm speaking to Andrew Philippides from the University of Sussex about visual navigation in insects and robots. Until then, I've been Claire Asher, and this has been Robot Talk. Robot Talk Season 6 is sponsored by the Hamlin Centre, Imperial College London.